Hello, my name is Diogo Gomes and I'm a professor at the University of Aveiro. Today I'm going to talk to you about gamification in training and how to motivate 21st century students through 20th century games. It is well known that there is a general shortage of computer science engineers worldwide. Digital job growth from 2020 to 2025 has been growing steadily, and data analysis, machine learning and AI is an important sum of these jobs. Artificial intelligence has gained an important momentum, with machine learning and artificial intelligence as general term accounting for most of the jobs opening in the AI area. Yet, very few students finish computer science degrees. So what are universities doing to tackle these issues? Universities teach students introductory AI classes. In these introductory AI classes, problem solving, such as traveling salesman or goal stack planning, are used as examples of AI applied. This becomes very challenging in keeping students motivated. Students are nonetheless not very much motivated to attend these classes, so it was important to realize what they're actually doing while attending the class. With the introduction of laptops into the classroom, students started to use their laptops for many other things other than attending the class, spending time on social media, watching videos on YouTube, or even playing games during class. It was very important to realize why are students enrolling in computer science programs. One aspect that jumped clearly was the fact that computer games are something challenging which they enjoyed during their adolescence, and there's something about them that drives students towards computer science. Computer games and AI are no strangers to each other. Games have traditionally been one of the main research topics in AI. In 1996, IBM Deep Blue was a major landmark in AI research when the algorithm developed by IBM won the chess champion Garry Kasparov. In 2016, AlphaGo, another algorithm developed this time by Google and DeepMind, won against Lee Sedol, the Korean champion, on the Go game. Board games are very challenging, but do students relate to these games? These games are not very popular when you're 20 or 21. Truth is, when students think of computer games, they think of games such as FIFA, CSGO, League of Legends, Fortnite, PUBG, games with fast action, live, and mostly with strong graphics content that immerse them into the real action of the game itself. If we are going to drive students towards AI through games, we must match expectations. AI is an introductory course at the University of Aveiro for third-year students. Students' programming skills at this time are average, but mostly centered in Java and Python. Existing game engines place a large overhead and are not the core to the course. Frameworks such as OpenSpiel focus on advanced AI techniques such as deep learning and are out of scope for third-year students. Therefore, the idea of using games to teach AI must stay with simple games that can be easily programmed and repurposed for learning objectives. Games such as card games, arcade games, Atari, NES are simple games that can be fun and yet repurposed with the objective of teaching AI. After years trying to figure out the best way to motivate students to learn AI, we decided to run a live experiment with the idea of running a game as the objective of the class. After years using a robot simulator called Cyberrato, in 2015, we decided to play a first experiment. We challenged students to develop a blackjack playing agent. This is a card game usually played in casinos. Students' grade would become proportional to their agent performance, with a minimum set of requirements to classify 10 out of 20 and therefore pass on the class. This created not only a game purpose, but also created a gamification of the class itself, with students that wanted to achieve maximum scores in the class needed to not only play the card game, but also achieve maximum performance in their agent. Students could still do Cyberrato assignment from previous years. This created a way of falling back if things would not go as smooth as we thought it could be. So there was a backup plan in either case. The results from this first year were already very interesting. Almost all students opted for the blackjack agent, despite existing code from previous years in the Cyberrato project, and students were eager to improve their agents. AI skills involved in developing a blackjack agent included minimax algorithm, developing a Monte Carlo simulation, and studying Bayesian networks. But some students actually went over the objectives and studied advanced AI algorithms to improve their agents. Some of them actually going into deep learning algorithms and machine learning techniques. The final grade in AI class was now a scoreboard. This was something that actually surprised us professors, because students were actually fighting each other to get the best grade in the class. It was not longer about passing the class, it was about scoring the highest and being the number one in class. This was also something that triggered a continuous assessment of the students about what is their position related to other students. They wanted to compare themselves. The gamification process was fully geared. This first experiment was very successful, yet things could be improved. Grading especially was very complicated. With about 70 agents developed by students, we were required to play about 1,000 games to avoid the impact of random events and sheer luck into the scores of these agents. Another important aspect was that agent and game agent code was tightly bound. So the agent was simple class object which students could tamper with, and we had to review the code that students submitted just to check if they were not cheating. It was still important to make sure that students that did not fully engage in the gamification of the class could score an average grade and pass the class. So we had to attend to these students scoring minimum KPIs in the game that could assess that they knew the basics of AI. After this successful first year, we decided to go with a more interesting game. We decided to retrofit a retro game. Retro games, normal retro games, are not usually accessible to computer AI students. They come in binary form and they are tightly bound graphics and motion and algorithms, so they're not very easy for students to manipulate the code to introduce artificial intelligence. They're pretty much monolithical. The UI is one of the big issues because it's bound to the execution environment. That disables any chance of automating tests and evaluation of the games from the students. So we retrofitted the Snakes game. In 2016, we introduced this game, made popular by Nokia on their mobile phones, to students through a Python-developed code base. We used the graphic engine Pygame, and we developed a client-server architecture that decoupled the agent that ran the artificial intelligence from the UI code from the game engine. We enabled students to play against each other on one-on-one games, and we created a scoreboard based on rankings using tennis ATP rules. This was unfortunately not a good idea for underperforming students, and we quickly learned that this is not the best way approach for gamification purposes. Snake students could see live action. Death matches in 2016 gave way to collaborative snakes in 2017 in order to attend to underperforming students. We thought that by making the game collaborative, we could have students more engaged and not suffering from the challenge faced with challenging very developed snakes by higher grade students. Nonetheless, this was still not perfect, and the scoring and grading purpose needed more refinement. Some very important lessons were learned from Snake. First off, that students went beyond developing the agent and actually got involved in developing the UI. So we here saw the room for points attributed to students that got involved beyond the basic objectives. Another important aspect was that ATP rules used to grade the students were not appropriate. So we needed to change the way that students are graded in the next year. Another aspect was related to the game engine itself. We developed the game engine for Snakes for the first time, and we finally found out that it was not the appropriate way of doing this in class. Basically because some student algorithms were very slow and would stop the engine. So they would benefit from actually spending more time running their algorithms than actually playing the game. So we needed to decouple the agent from the game engine itself in the next year. As for AI topics covered, we basically covered everything plus one. Students learned about search algorithms, A-star algorithms, greedy, deep first, but also jump point search and minimax, which were out of scope of the class. In the next year, with all these lessons learned, we developed a new game, Pac-Man, the classic game, through a new asynchronous engine that fully decoupled the artificial intelligence agent developed by the users, in this case the students, from the actual game itself. This way the game would run at a continuous speed regardless if students' algorithms were stalling or not. The new asynchronous engine allowed us to achieve yet another goal, which was to detach the viewer from the game engine. Detaching the viewer from the game engine allowed us to run the code in the cloud. That meant that instead of running the computer game from students in a computer with the screen on and checking everything that's going on, we could now run in the cloud completely headless and score automatically the game. Students can also run their code independently and have a baseline score that gives them a passing grade. So students can know from day one how much score do they need to achieve passing grade, and they can compare the score between themselves and know relatively how good are they scoring in the class. AI topics covering Pac-Man were again a very success, as we covered all search algorithms in the program, A-star, greedy, deep first, but also jump point search and minimax. This was actually something that is exactly the same as in the previous game. So in the next year, we decided to change things a little bit again in trying to increase the type of algorithms involved in the game. In 2019, we took in the game Bomberman. It was still based on the previous year engine, but we added more actions and keys to the game in order to increase its complexity. So beyond the arrow keys, now you had to deploy the bomb, and this basically made the game pretty much different from just scrolling around in a random maze. Bomberman server was publicly available to students. That meant that they could run independently their code, but they could also share publicly with all remaining students. Students immediately adhered to this initiative, and a few weeks after they started working, we could see their scores in the public server, and they were fighting each other to be in the leading. Students got completely fully engaged into the class. Week after week, the agents got better and better, and since the scoreboard was public, everyone kept a tab on their browser looking who's in the lead. AI topics, again, were basically planning, search algorithms, A-star, greedy, and deep first, and jump point first. Bomberman saw the introduction of planning, and planning was a very important aspect for the leading agents. So in the next year, we decided to increase the role of planning into the game. In 2020, we introduced Sokoban. With a new and improved engine, this engine enabled us to be even more automatic. The game improved in quality, but also in features that enable us to replay the games on the students. This was very important so we could reproduce and describe to students what was going to happen during the evaluation process. Sokoban used competition grade maps that we downloaded from sites where fanatics of this game, classic game, actually keep difficult maps in. Students found papers about these maps and actually implemented those algorithms. This was a very big success because this drive them to read scientific papers, not a very usual thing to see in third year students. Algorithms, of course, here were more centered around planning, and search algorithms were basically just A-star. But let's go into detail of how things are implemented and how to make a retro game accessible to AI students. First off, the most important aspect is the architecture of the software that we developed in order to enable this gamification. Games are implemented using a client-server architecture in which we have a server that runs the game logic and a client that runs the AI agent. The viewer we detached from the server by creating yet another client, but it's a special client that just runs the GUI. It does not send any events back to the server. The server provides a WebSocket interface to both client and viewers pushing game state updates synchronously. So clients update the AI agent state and provides actions such as key presses, while the viewers, they just update the screen. The use of the WebSocket interface meant that these games can be run over the internet. This is something that we want to address in the future because some opportunities might arise to run actual hackathons or game events around these games. Upon game over, the server issues an HTTP post to a score server containing information relevant for student grading. That basically depends on the game, but involves things such as the score, the lives, the time spent in the game, the number of steps the agent had to give, etc. All grading is run automatically in the cloud. So each student agent is orchestrated into a container and several servers can be spawned to run in parallel, reducing grading time. From the initial game in Blackjack and in Snakes, where we had to run the game in full screen and we would have to wait until the agent played the full game, we went into a new scenario with the latest game engine where we can actually run hundreds of servers in parallel in the cloud and efficiently get the grading in a few hours. The representation model is very important in this game. It is very important that the students only need to deal with basic models and don't need to deal with pixels and information spread around the screen. So students can get access to the state of the game through a simple JSON document. JSON is the best choice because it's easily parsable in Python, it's human readable, which makes it easy to debug, and it's a well-known technology for the students. The JSON document contains information such as the coordinates of the agent, involves coordinates of important aspects. In Pac-Man, it involves the coordinates of the ghosts, but also involves the coordinates of the pellets. So everything is just described explicitly through the JSON document properties. Actions that the agent does are actions of the humans. The agent cannot do anything else besides simulating the pressing of a key. The pressing of the key is simulated through a single JSON message containing that key. That means that if you want to press the same key several times, you would actually need to send several times the message. This was very important to make sure that we could detach the key pressing from the actual game engine itself, compared to the year that we had the Snake, where students would take a long time pressing the key and would take advantage of those situations. We didn't just use a game for teaching AI, we also put in gamification into AI class. The gamification is achieved through a public high score table with KPIs that keeps student progress. We keep information about each run of each agent of each student, a very large database that we can sort and remove statistics from it. We know how many students have reached the end of the game. We know what has been the minimum score in each level, and we know how intelligent each agent is based on their KPIs. To score the students, we develop a linear equation that goes from the basic achievement of objectives, scoring a number of points, goals, or just cleaning up the first level, up to the student which got the most points or best score achieving the last level of the game, which would be graded with a maximum grade of 20. So between 10, which is the passing grade, and 20, students are spread linearly based on their scores. All that you have seen in this presentation is available as open source. You can find all the games and all the software necessary to evaluate the students in the GitHub repositories presented. Besides scoring the students based on their agents, we also encourage students to contribute, providing them extra credits for new features. That made it possible for students that do not score high enough on their agents to get maximum scores thanks to these extra credits. Evaluation is carried out through GitHub Classroom. We have each group owning their own project, which is private, and they keep it private for the duration of the semester. Afterwards, they can make it public. Usually they do, and they like to share with recruiters. And on the deadline, GitHub Classroom will just collect all the code, zip it, and I'll be provided with a zip file, which I can use with my scripts to run on the cloud. The server runs the game headless 10 times per agent, and we average the results to give the final scoreboard. In conclusion, we didn't invent anything new. This whole idea of running retro games and gamification has been explored by Gettysburg University. We did get students involved with games that they never played before, and this was very amusing because they were born in an age where these games were already very ancient. Attention to class and time spent in the project increased a lot. That also meant that some of our colleagues from other courses complained a lot, complaining that students were spending most of their time developing the code for the AI class and not doing the other tasks. Some students actually did the next year project for fun. So after finishing the course, they came back the next year and asked if they could run also the project together with the next year's students. Motivation has clearly increased. So what holds the future for these students? This class opened the door for many of them. Participation in hackathons such as Global Game Jam increased by tenfold. We also will try to explore how to use both games and gamification in other subjects to increase class attendance and the drive to attend class. And students are on their own planning and running their own hackathons, which clearly says that this has been a success. Thank you so much.